Welcome back, everyone. Today we're going to be talking about statistical samples, and in particular, the properties of those samples. A statistical sample is a set of observations from a population that we can use to draw inferences or conclusions about that population. So for example, if we're interested in the abundance of Bythotrephes, this nasty little zooplankton in a particular lake like Fairy Lake, we don't have to measure all of the Bythotrephes in that lake, we can sample. So let's say we go out in a boat and in 10 different places in that lake, we drop down the net and we lift it up. And for each of those net pulls, we record how many Bythotrephes are present in the net. And that's represented by this set of 10 numbers corresponding to each of the 10 net pulls for which we counted the abundance of Bythotrephes. This set of observations then represents our sample. We can use that sample to then generate an estimate, in this case, of the abundance of Bythotrephes within the lake. The average of these 10 values is 50 Bythotrephes per 0.2 meters squared of the lake. And that represents an estimate of the abundance of Bythotrephes in Fairy Lake. So what we want to do today is to talk about three different aspects of statistical samples: sample size, sampling error, and bias. Sample size is perhaps the easiest one to think about. It's simply the number of measurements in your sample. So for example, in our sample for Bythotrephes, we had 10 observations of Bythotrephes abundance. Our sample size is 10 net toes. In other instances, we might have measured the water chemistry in 12 wetlands, or perhaps the expression of 32 genes, or maybe the growth rates from 10 tree cores. The second aspect of a sample that we're going to talk about today is called sampling error. Sampling error is simply the random differences between the true population parameter and our sample estimate that are just due to chance. If you were to ask me how much milk I had in my fridge, I could go over to the fridge, look inside, and figure out that there are 2 gallons of milk in the fridge. If you were to ask me to go back and do that again, I would walk back to the fridge, open the door, and see that there are still 2 gallons of milk in the fridge. That's because each time I go and measure the amount of milk in the fridge, I'm measuring everything that's there. I'm measuring the entire population. But in statistics, we never measure the entire population. We only measure a sample. And each time we sample, we get a slightly different subset from the population. And as a result, our sample estimates are slightly different. These differences among samples from the same population, just due to random chance, is what's referred to as sampling error. In the example that I introduced at the beginning, we had an estimate of 50 Bythotrephes per 0.2 meters squared of lake. But what if we were to repeat this sample, again with 10 observations from different locations in the lake? So let's try this. Let's do it again. And what do we find? We get a different sample that isn't exactly the same. Each of these samples is slightly different. And the reason for that is that each of these is representing a slightly different subset of the overall population. And just by random chance, one subset might be slightly larger, the other might be slightly smaller. What if we were to do this many, many times? What if we were to go through this same process of collecting 10 net pulls, calculating the average of those 10 to come up with an estimate for our sample, and repeat this 1,000 times? What we might find is something like this. This is a histogram. In a histogram, the height of the bar represents the number of observations, in this case, the number of samples, that have a particular value corresponding to the value on the x-axis. So in this case, we can see that most of our samples are going to come up with an estimate in and around 50 Bythotrephes per 0.2 meters squared of lake. But in some instances, just by random chance, we can actually estimate very low levels, or very high levels. Each of these samples is itself based on a sample size of 10 observations, so that hasn't changed. But even still, just by random sampling error, sometimes we get values larger than normal, and sometimes we get values less than normal. And this spread in our estimates, this variability in our sample estimates, is what's referred to as sampling error. Now, this isn't any sort of mistake on the part of the experimenter. You haven't done anything wrong here. This is just a fundamental principle of sampling. Because we haven't measured everything in the population, each time we do it, we're going to get a slightly different answer. So how can we deal with this sort of sampling error? Or is there anything that affects how big this sampling error is? Well, in fact, there is. All of these samples came from a sample size of 10 net pulls. What if we were to repeat this whole exercise, but instead make each of our samples have a sample size of 25 net pulls instead? So here's what that histogram would look like, shown in blue. Each of the 1,000 samples was based on a sample size of 25 net pulls instead of a sample size of 10 net pulls as shown in the figure on the left. And the difference that you can see is that the variability among those samples, that is the sampling error, is much smaller in the blue histogram than it is in the red histogram. And this reflects a fundamental principle of sampling error. The larger the sample size, the smaller the sampling error will be. And this is due to what's called the law of large numbers. Larger samples will tend to have lower sampling errors than smaller samples. We can depict sampling error using a bullseye plot like I've shown here, where the bullseye or the target is designed to represent what the true population parameter actually is. Now remember, we don't ever know what the true population parameter is. We're trying to estimate it from our sample, but this figure is designed to show us hypothetically what it might look like, where the true population parameter falls in the yellow part of the target, and farther values away from that are represented by the outside circles. So you can see then that when we have low sampling error, each of our samples, shown by each of the black dots, is fairly close to the true population parameter and are close to one another. They're very consistent or very precise. In contrast, when we have high sampling error, there's a lot of variability among the estimates in each of the samples. They're all still centered around that true value, but there's a lot more spread around them. That is, they are imprecise. The third property of samples that we'll talk about today is called bias. Whereas random differences between sample estimates and population parameters is referred to as sampling error, consistent differences between the population parameter and our sample estimate is referred to as bias. That is, consistently underestimating or overestimating what the true population parameter is. Bias can come from two sources: measurement bias or sampling bias. Measurement bias comes from flawed measurement tools or equations. So for example, if our zooplankton net had a mesh size that was too large and allowed some Bythotrephes to slip through the net, then we would consistently underestimate the true abundance of Bythotrephes in the lake. But beyond these measurement biases, there are more important biases to pay attention to, or at least more common biases that occur as a result of sampling bias. Sampling bias occurs when some individuals in the population are more likely to be sampled than other individuals. So in terms of our target plot then, when we have unbiased estimates, all of the sample estimates are clustered close to the true population parameter shown in yellow. In contrast, when we have a biased estimate from our sample, all of the sample estimates might be close together, but they're consistently too high or perhaps too low. And as a result, we have a poor estimate of what the true population parameter is. The word that we use to refer to unbiased estimates are accurate, and the contrast to this would be inaccurate or biased estimates of the true population parameter. We can combine bias and sampling error together into this 2x2 plot. In the top left panel, we have samples that are both accurate and precise. That is, they're very consistent and centered around the true population estimate. In contrast, we can have high sampling error with imprecise measures that are very inconsistent and deviate quite a great deal from the true population parameter, but not in any consistent way. They're not consistently higher or lower, and that is that they are accurate but imprecise. In the bottom left, we have very precise estimates in that they're very consistent, but they're consistently wrong or consistently inaccurate. And finally, in the bottom right, we have the worst case scenario, which are estimates that are both inaccurate and imprecise. So in summary, sampling involves the measurement of some, but not all things from a statistical population. And as a result, each time we sample, we measure a slightly different subset of the population, and these samples will vary. The sample size is simply a measure of the number of things that you have recorded. Sampling error are the random differences between samples that you get as a result of measuring a subset of the overall population. Samples with larger sample sizes will tend to have lower sampling errors, while samples with smaller sample sizes will have larger sampling errors. Finally, bias represents samples that are consistently too high or too low. And these biases can result from biased measures or biases in our sampling design.